Thank you very much. I'm here today to talk about Clojure, which is my favorite new language on the JVM. So what is this talk going to be about? I'm going to talk about what I'm calling Clojures for elevators, the things that elevate it above other languages on the JVM, the way that it does Java interop, that it is a Lisp, that it is functional, and it has a unique state on state and concurrency. And I'll talk a little bit about the ecosystem, but really what I want to show you is what really sets this language apart from all the other languages that you can choose on the JVM right now. So what is Clojure? Clojure is a dynamic, strongly typed, functional, high-performance implementation of a Lisp on the JVM. It's dynamic, it is strongly typed, but it's dynamically typed, which means that it knows what type things are, and you can do reflection on them, but you don't have to pre-declare types beforehand. It is dynamically typed. It is very much like Groovy and Ruby and Python in that way. But it's also a functional programming language. The primary paradigm here in Clojure is functional programming and functions. And that makes it an interesting entry into the language category, especially when you compare it to something like Scala, which is the one that it's most often compared to. And let me talk a little bit about the difference between these two languages. Scala, in many ways, is trying to build a destination that includes a bridge. So Scala is trying to get you from where you are to where you should be, which is you're now an imperative object-oriented developer, and you should be more of a functional programmer. And Scala has got this nice fat bridge to help you do that. It supports objects, it supports functions, it supports procedural coding, and is therefore a tad dangerous because it supports all these different paradigms. Ruby is like that too. It supports a lot of different paradigms, and it takes a fair amount of discipline to just use one and use the correct one for a given situation. Clojure's not trying to build this bridge for you. They're building just a destination. And so the decisions in the Clojure world are not as much to do with, can we make things nice and easy for the transition? It's what's the correct thing to do from an engineering standpoint. We'll make it so that you can call into the entire Java ecosystem and have full access to that platform, but we really want to support a kind of a la carte set of abstractions so you can mix and match them any way that you want. It's also very high performance. One of the goals of Clojure is to create a very high performance language, and it is. It is on par with languages like Scala on the JVM. In fact, with some tuning, you can get it close to native Java speed, as some of our clients have at financial services companies in New York, because they're very interested in concurrency, and they want to do things in Clojure as well. In fact, Clojure is written very close to the metal in Java. The traditional way that you implement a Lisp is a particular structure called a console. Rich decided not to do that in Clojure. This is his fourth or fifth Lisp implementation, and he decided as the core abstraction at the bottom of Clojure is going to be Java Lang object. And a lot of traditional Lispers kind of saw that and kind of poo-pooed that decision early on, and then they saw the performance of Clojure on the JVM and said, you know what, that's probably an okay decision, because it made the performance really, really nicely tied to the JVM. And it is a Lisp. Now, isn't the Lisp the one with all the parentheses? Yes, it is. Which begs kind of an interesting question. There are over 200 languages on the JVM that you can choose from now. So why would you pick one with this odd syntax, and why would you create one with this odd Lispy syntax unless there was some really compelling advantage to it? And in fact, there is. Lisp is a homoiconic language, which is really just a fancy way of saying that Lisp programs are also Lisp data structures. That sounds like a really minor thing, but it turns out that it's not. It turns out that this gives you unprecedented power when you're doing metaprogramming in an environment like this, because metaprogramming is just programming in a Lisp. It's not a special thing that you do that's extra programming. It is just like regular programming. It turns out this is crazily useful, and I'll delve into why this is so useful in a couple of ways during the course of this talk. First, I want to talk briefly about the ecosystem. If you're curious about Clojure, you need to know how to build web applications and how to do builds and stuff like that. Clojure is an open source language that's supported by Clojure Core. It uses the same model as a Spring and Red Hat, where they give you bits for free and they sell consulting and training and that sort of stuff. They're actually funding development of the counterclockwise Eclipse plugin. So if you want tools to do Clojure coding, there is a great Eclipse plugin called Counterclockwise that Clojure Core is actually maintaining and paying to have maintained. So it's a really nice Eclipse plugin that gives you a REPL, which is very common in Clojure within the Eclipse environment. Or you can go really old school and do Emacs. That's actually one of the things that, one of the classic tools for doing Lisp development. And in fact, Emacs has a couple of facilities that your fancy IDE doesn't have when you're coding Lisp. Because it's a homoiconic language, the editor understands the syntax. There's this really cool mode called par edit mode that actually lets you manipulate S expressions with hotkeys, kind of like refactoring, but in a slightly more powerful way. It's more like prefactoring. The build tool of choice in the Clojure world is a tool called Leiningen. This does the work of both build and transitive dependency management. So this is your Maven in this world. It'll handle transitive dependencies for you and also do build tasks. And there are a bunch of other things in this ecosystem. It's a modern, mature ecosystem. There's a web framework called Composure that's based on Ring. There are several different persistence libraries. There's a partial port of active record from the Ruby world and the Clojure world. There's a Clojure QL, which is relational algebra to SQL mapping. There's also Clojure Script. Clojure was designed to be a hosted language, and in fact, it runs on Java, .NET, and partially on JavaScript. And this is not a CoffeeScript kind of a thing that transpiles into JavaScript. They've actually implemented Clojure in JavaScript. Now, it doesn't do everything that Clojure does. You can't do threading in JavaScript, of course, but all the rest of the syntax for Clojure works on top of JavaScript as well. They've written a Clojure interpreter as part of JavaScript. So let's look at some Clojure code. The data types in Clojure are very closely aligned to the Java data types. In fact, the string in Java is exactly the string in Clojure because Clojure likes Java strings. It's immutable, and Clojure loves immutable things, so there's no reason to re-implement string if you've already got a good high-performance immutable string there. We have characters which map to characters. Patterns are first-class citizen, and in fact you have syntactic sugar for regular expressions like this. Pattern actually uses the underlying Java abstraction, but matcher, the thing that comes with pattern, Clojure has written their own because bizarrely, matcher in Java is mutable. It shouldn't be, and that's weird, and so Clojure wrote their own matcher, but they're using the pattern class that Java provides because it is immutable and has the characteristics that Clojure likes. We have artificial arbitrary precision integers that automatically escalate, so you don't have to worry about rollovers and stuff like that. If you're dealing with ints, it'll automatically roll up to longs. We have doubles, and we have arbitrary precision doubles. We have a Boolean, which is true, which maps to Booleans. Neal is Clojure's versions of null. We also have two other things that Java lacks. Two ways to name things. Java kind of has symbols in the way that we use them as variable names. So symbol is really just a name for something. So method names are symbols, so that's the name of something. We also have this special thing in Clojure called a keyword, which is a symbol that has a colon in front of it. It's really just a constant string, but these are used often as map keys. That's the key part of keyword, not like language keyword, but as in key for a map. And so these as strings are frequently used as map keys. Both of these just represent the thing that you're talking about. So for example, in Java, when you're trying to load a class through reflection, you have to represent that class name as a string because Java has no way of referring to the names of things. Clojure has two ways, symbols and keywords. We have data literals in the Clojure world, and we have Lisp. This is the core data structure in a Lisp. And this is a singly linked inserted front list that's delimited with open and closed parens. But Rich added another list data structure to Clojure as well. He added vectors. And these are indexed and inserted rear. And he also used vectors in a couple of key places in the syntax to clean up the syntax, to get rid of extra embedded parentheses that are kind of annoying. So we'll see those actually pop up in a few places. So we have lists and vectors. We also have maps. Maps are key value pairs. Anything can be a key and anything can be a value. Very often keywords are the keys, but that's not a requirement by any stretch. And of course we also have sets in the Clojure world. Here's what a function call looks like in the Clojure world. This is the name of the function, and this is its first argument, and it might have some other arguments. I know this is really freaky. What we've done is taken the parentheses and move it from here all the way back here. Don't panic, it's okay. We just moved it one character back, it's the same thing. But there are actually some huge advantages to moving that parentheses one character back. So when you look at this, the semantics of this is a function call and it takes an argument. Remember I said earlier that Clojure programs are also Clojure data structures? And so if you look at this from a data structure standpoint, this is a list and a symbol and a string. So it's actually both things. Here is a slightly more elaborate function definition, or an actual function definition, not a call. I'm defining a function called greet. This doc string is a string that describes what it does. This is optional, but in the documentation facility, this comes up as a summary, and then you got 4 docs down below that you can fill in the names for. And in Clojure, the arguments to the function go in a vector. Now in traditional Lisps, this is another embedded list with parentheses, and when you get these things nested together, they're hard to read. By making the argument list a vector in Clojure, it sets off the arguments much better and cleans up the syntax just a little bit. And now you'll have as many lines of code as you want. These are just a series of function calls, a function and a string and an argument. You can have as many of those as you want as part of the function body. But again, we're in a homoiconic world, so if we look at this from a data structure standpoint, it's all just the data structures that we've already seen. In fact, we've seen pretty much the entire language now from a building block standpoint. Now, I mentioned earlier that Clojure is dynamically typed. There are some situations, particularly when you're doing interop with Java, that you'd like to provide some type hints. And Clojure will allow you to do that, like this. In front of a method declaration, you can put a type hint, and that basically says this is expected to return a string. This is really handy if you're interoperating with Java and need to send it some type hints for something. So you can type hint. This doesn't speed anything up from a Clojure standpoint, but it makes interoperability with Java a little bit easier. So that was a named function. What do anonymous functions look like? Well, they're functions without a name. It's function and then whatever parameters you pass in. And so what that's doing is multiplying x times x. This is basically an anonymous function that squares whatever number you pass into it. So for example, let's say that I wanted to call the map function. Map expects to take a function and a collection, and it executes this function on top of every element in the collection. And so this function basically says square all these guys, and when this comes back, it's going to come back with 1, 4, and 9. But functions show up a lot in Clojure, and so this is kind of cumbersome when you have a single parameter. It shows up over and over again. And so there's some syntactic sugar in Clojure. If you have a single parameter, you can actually declare the anonymous function like this and use the % sign as a placeholder. So the same map operation would more idiomatically be written like that. Map this anonymous function onto that vector. So let's talk about decisions. Here's a function that decides which of the two is larger than the other one. The if statement here takes a condition that returns true or false. If it's true, it returns the first value. If it's false, it returns the second one. So there's the true branch, there's the false branch, and of course those can be as many lines of code as you want, wrapped in function calls inside a parens. And so here's an example of actually using this as the REPL. There's my larger, and I can say the larger of 4 and 12 comes back as 12. But let's say that you have this larger, and now you want to make sure that you get a larger number and you have a non-negative value. So you can nest if statements together. If there's the condition, this is the return for the true branch, and that's the return for the false branch. So you can see kind of how the code knits itself together like this. But let's refactor this and clean it up a little bit. In fact, my larger and non-neg, I'm going to rewrite in terms of the larger function that I had before, because what I want is the larger of 0 or the larger of x and y. So that's actually a larger function, or larger and non-neg. But let's look at larger. I have two arities, which means I can pass in two values, but why not give me the opportunity to pass in as many as I want? This is Clojure syntax for multiple parameters. The ampersand means I have more parameters, and this becomes a list that it packs all those extra parameters up in that list called more. This is really handy because the ampersand packs them all up into more, and then apply just unpacks them. So that's basically what we're doing there. And what this is going to do is support any arbitrary number of arguments that you want to pass to it, and it'll give you the larger one back. So does that cover everything? Well, there's an edge case here where we might want to cover a single value as well. If I pass in a single value, then the larger of it is going to be that value. And you think about this a lot in the Clojure world. Can we handle all these different arities? And so now discover that the function that we want already exists. There's already a max in Clojure, which is not surprising. And it has performance optimizations that make it more sophisticated than mine. And in fact, add a REPL in the Clojure world. Anytime you want to see the source for a function, just call the source function on that symbol name, and it'll show you the source code for it. So if I come in here and say source of max, here's the definition of max from the Clojure world, including being smart about optimizing for native types if you have certain things going on to make it more efficient. So let's talk about the Java interop story with Clojure. I mentioned before that Clojure allows you to reach every single piece of the Java ecosystem, so let's see what that looks like. You get to all of Java. Clojure compiles to bytecode. This is not an interpreted language, so it is fast. It's a really high performance language. You can also call Clojure from Java. This is a little bit tougher because you have to adhere to Java's rules about immutability and things like that. But it is possible to call Clojure from Java. It is just bytecode after all. But the much more common case, of course, is to call Java from Clojure because you already have tools that you want to use. So let's look at some side-by-side comparisons. Here's how you construct things. In Java, you say new widget. There's syntactic sugar in Clojure. There's a class name dot. That fires the constructor, and then there's the constructor parameter for it. If you want to get to a static member in Java, it's class name dot constant value. In Clojure, it's class name slash constant value. If you want to get to an instance member, if you say round.nextInt, the way that you do this in Clojure, the function always comes first in Clojure. The first position here is always a function. And so what you do is just make the object the first argument of the function. So if you'd normally call rand.nextInt, you'll call .nextInt on rand. And if this took any extra parameters, these would be the second, third, through the rest of those parameters to that function. So you're basically just flipping the function call around and taking the object as the first parameter. One of the really common things in Java is a great love of violation of the law Demeter, where it's this, dot this, dot this, dot this, dot this, person.getAddress.getZipCode. That would be annoying if you had to do it all kind of inside out, but Clojure has syntactic sugar for that too, because they know Java developers do this a lot. So if you say dot dot here, it'll basically chain all those together as if you had this chain of person dot do this, dot do this, dot do this. You only need two dots, and you can put as many calls as you want there, and it'll just chain them all together for you. I'm sorry? The function name doesn't, well, actually it does because this is a macro. So it is still the function, it's just the macro function that's taking care of that. So it is still kind of a function, it's just a different function than the one we're actually calling. Because it'd be kind of annoying, you have to call it inside out. You have to call get zip code on get address on get person, and that's not the way you think about it. So this lets you kind of rearrange it in the way that you think about it. It makes it nicer. So one of the things that people complain about Clojure is it has too many parentheses in it. But let's do a count of parentheses so far in the Java interop stuff. The Java code that we've looked at so far has 8 sets of parentheses, and the Lisp code only has 6. So there. Clojure has actually done a lot of work to clean up the syntax and get rid of too many nested parentheses, because that's one of the annoying things in a Lisp, and Rich has done good work to get rid of those. Clojure can reach to all these different parts of Java. So for example, let's say I wanted to implement an interface. That's the reify function in Clojure. You reify a Java interface. Runnable requires a single run method that takes no parameters. There's the body for it. If this actually had 4 or 5 method signatures in it, I'd have 4 or 5 method signatures right here that would implement a class that is runnable as a thread. And you can add more interfaces there later if you want. But I want to start trying to show you some of the power of Clojure. And I'm actually going to do this kind of experiment twice. I'm going to take a method that you're probably using in your code base somewhere, the Jakarta Commons, Apache Commons is blank method, and I'm going to port that over to Clojure one small piece at a time. So here's the isBlank method from Apache Commons. This is you pass it a string and it tells you if the string is blank or not. So it does a couple of edge cases, null and zero length string, and then it goes through each character at a time, and if it finds something that's not a white space, it returns false, then it returns true. So let's move this over to Clojure one piece at a time. So the first thing I'm going to do is get rid of the types, because Clojure is a dynamically typed language, so it can strip away all the types and squeeze things back together. The next thing I'm going to do is get rid of the class. We're in a functional-based language, not a class-based language, so this is just going to be a function. It's not going to be inside a particular class. Now I'm going to use a higher-order function. This iteration is almost always a smell in a functional language because you can use a higher-order function instead. And so I'm going to replace that iterating one character at a time with a much smarter higher-order function that says, give me every character in the string, and then return, if character is white space, then it'll return true. So notice we're not in either Lisp or Java right now. We're kind of in the middle between those two because we're transitioning. Now I'm going to get rid of the corner cases because it turns out the higher order functions in Clojure automatically handle the null case and automatically handle the zero case for me. So I don't have to do anything special for those edge cases. So I can get rid of those guys. And now all I have to do is Lispify it. And there's what blank would look like in the Clojure world. The question mark is part of the method name, and that's an indicator that this returns true or false. That's just a naming convention. It's not required, but it's a common naming convention in Clojure. And notice how well this reads, despite being a Lisp and all the weird syntax. Blank question mark of a string, the definition is that every character is white space. That means it's blank. So in some ways, this reads really nicely. It reads very much like the abstraction that you're going after. That's one of the real goals in Clojure, is to write really, really readable code. In fact, that's super readable. I don't care how experienced a Java developer you are. If I didn't show you the name of this class and this method and showed you the code, it would take you a few, maybe 30 or 45 seconds to figure out what it does because there's just so many meaningless details down in there. This is pretty clear what it does, because it's been written to be nice and readable. So what's so special about a Lisp? Paul Graham has a great essay called Beating the Averages where he talks about language features. And he splits them into industry norm versus Lisps. And I further subdivided them into kind of the common cool kid languages. So the industry norm languages have these 4 features in them. If you look at the cool kid languages like Groovy or Python or Ruby or Scala, they have these extra features like a function type and a symbol type. The whole language is available, means you can do really good metaprogramming. But there's only one that has this last tick, which is homoiconicity. Only Lisps are homoiconic, and so none of these other cool kid languages can make that claim. So why is that so important? I need to talk for a second about special forms. Special forms are the syntactic scaffolding for your language. So that's the imports and the scopes and the protection. This is the if statement in Java. Notice that the if statement in Java, you can't change how that works. In fact, when you learn Java, one of the things you had to learn was, here's the if statement. Here's how it works. It automatically short circuits. There's an optional then clause. You have to learn about the dangling else and all that. That's part of learning Java, is to learn how these special forms work. The if statement, the while, what a class structure looks like, etc. Those are all the special forms, the scaffolding for your language. Special forms outside of Lisp are different from ones inside Lisp because they're limited to very specific use. A while loop doesn't have much flexibility. It is pretty much for iterating over a collection and not much else. These things look different than the other things. You can't create new statements in Java. You can create new methods and call them, but you can't create something that looks like an if statement in Java. A lot of them have semantics unavailable to you, like the way short-circuiting works and Boolean operations in Java. And at the end of the day, they actually make things harder to use rather than easier to use. Because what happens is, when you have a lot of special forms, they start interacting with one another in all sorts of interesting ways. Lisp special forms are different from other languages because they look just like everything else. And they may have special semantics available only to you, not restricted to you, but available only to you. And you can augment these guys with macros, which I'll talk about in a second. Notice that all the special forms in Clojure look the same, because a function call is a list, an operator is a list, a method call is a list, an import, well, you get the idea. They're all lists. They all look exactly the same. So why is this an important thing? Special forms are easier to understand individually, but create combinatorial complexity when you aggregate them together. To deal with that complexity, you start categorizing things, and you eventually end up with things like design patterns, which in some ways are kind of band-aids for a poor language design. We don't use design patterns in Lisp almost ever. In fact, there's an alternative to this, a reuse mechanism in Lisp, and it's this idea of a macro. So let me explain how Lisp macros work. So let's say that you have this code. You're building a swing application in Clojure, you have a frame, and you need to call the add the panel to the frame and pack it and set visible. That frame thing showing up over and over is kind of annoying. I don't like that kind of repetition in my code, and I'd love to be able to metaprogram it away, make it look cleaner. And that's easy to do in Clojure. I just create a do to frame, and now each of these things applies to frame, and now this returns expression so I could do some extra things to frame if I want. Do to is already built into Clojure, and it's implemented as a macro. A lot of the features in Clojure are implemented as macros. How can you tell which ones are macros and which ones are just regular functions? You can't, and that's the point. There's only one thing in all of Clojure that decides if something is true or false, and that's if. But Clojure would be annoying if you didn't have if and while and then. So they've built macros on top of if that do all those extra things. But there's only one core mechanism in the whole language that handles truthiness. And that's actually very characteristic of Clojure. Clojure is this tiny, tiny, tiny little kernel of a language that they've built all this syntactic sugar on top of with macros to make it much friendlier to use. So here's an example of a sample macro. When x, print out whatever the body of this function is. When doesn't come with Clojure, or it actually is included with Clojure, but let's say I wanted to write it myself. Here's a macro when that takes in a test and an optional body. When I expand this macro, it expands to this. So let's look what happens when this expands. So when I call when, it's going to fall into this macro. It's going to take the test and the body. It's going to return a list. The return value of this macro is a list. And the first element in the list, the tick means leave the if there as a literal placeholder. And so the first thing in the list that's returned is that if, and then the test that I passed in is there. And now con says construct a list, starting with this element, and use that as the remainder of the list. That's going to con body onto this do, which is going to have all these lines of code there. Notice what the return value of this macro is. It's a Clojure data structure. This is homoiconicity in practice. If you want to do metaprogramming in Groovy, you have to learn about the expando meta class and category classes. If you want to do metaprogramming in Ruby, you have to learn how singleton classes work. If you want to do metaprogramming in Scala, you have to learn how implicit defs work, how virtual classes work, and how syntactic sugar works there. If you want to do metaprogramming in Clojure, you just write Clojure code. There is no special syntax in Clojure for doing metaprogramming because it's all just Clojure code. Everything is Clojure code. The macros are Clojure. The thing it returns is Clojure. That's the benefit of homoiconicity, because in Clojure, you can actually do transforms on your abstract syntax tree as metaprogramming. You're actually modifying the code directly. There is no more powerful metaprogramming facility on earth. Groovy gives you a tiny bit of this with AST transformations, which are hooks in the compiler that you can hook into to do some of these kind of transformations, but they don't give you the entire AST. You are actually coding in the abstract syntax tree in Clojure. That's why you have to have all the crazy parentheses, because you're coding in the AST, which means you can do these kind of transformations at the AST level if you want to. So there's a bunch of really useful macros built into Clojure. When is built into Clojure, so all these control flow, when not, and, or. Variable definitions are all handled by macros. Java interop, there's that ... function I was talking about before. That's a macro that handles Java interop for you. Rearranging things so you can re-spool them in the order that you'd like them in. Scopes, special forms, everything, all expanded code. So there's a special phase in Clojure, the reader macro, that takes care of all this macro expansion before it actually starts executing the code. So you're going to get the fully expanded version when you start executing it. So one of the things I was talking about Clojure is this is a functional programming language. So let's talk a bit about how functional changes the way you think about things. Here's the second instance of me converting something from the classical Java world into the Clojure world, and this one is even more impressive, the result, I think. This is a more ambitious method from Apache Commons. This is the index of any. So when you call it, here's how it works. When you call this on a string, you can say, give me the index of any character in this string. So the first occurrence of Z shows up at position 0. The first occurrence of B here is at the 3rd position. So that's what this thing does, is give you the position of the first occurrence of one of these guys that shows up in a string. And I want to take this and port it over to Clojure. So here's the implementation from Apache Commons. First thing I'm going to do is come in and simplify the corner case up at the top. Again, my higher order function is going to handle this stuff, so I don't have to worry about that. So I'll come up and just say, when I have search chars, that'll take care of the 0 case and the null case. As long as I know that I have search characters, I can go on. I can get rid of all the type stuff. I don't need all the type stuff, so we can strip all that stuff out, get rid of the type declarations. Now I'm going to come in and add a second when clause down here and replace this guy. Again, anytime you have an iteration, you can probably replace this with a higher order function. And I'm just going to replace this and say, when I have this, when you find this search character of ch, then return I. That's the index of that search character. Now I'm going to go in and replace this very last if statement with a list comprehension. This is kind of the Swiss Army chainsaw in Clojure for dealing with collections and pulling them apart and doing cool things to them. It has for, which looks kind of like a for statement, but it's not at all. This is actually a list comprehension. And what this says is, for the index and character in index string, what index string does is take a string and return it indexed. So if you have the string hello, this is going to return 0h, 1e, 2l, 3l, 4, etc. So that's what index string does. So this is going to return me the index and character for the index string, and then when I find a search character, return that index value. And now I'll Lispify it. And I actually made it a little more general when I Lispified it. I'm not looking for just any kind of criteria here searching. You can pass in any predicate and apply that predicate to try to find something in this collection. And again, once you know how to read this, it says, for the index and element that comes from the index collection, when the predicate of element is true, return the ID. That's kind of the way you read that, by interpolating inside those parentheses. But now that I have this, which version is simpler? The Java version has 18 moving parts. The Clojure version has 4 moving parts. And yet, the Clojure version is more general than the Java version. Because in the Clojure version, you can actually index filter on any collection. This basically says, I have a string of head and tail calls, index filter and return me the positions of all the heads. So there's 2, 4, 8, and 9 are all heads. Here is give me index filter on numbers that are greater than 1,000 that come from the Fibonacci series and give me the first one of those. This is saying that give me the first Fibonacci number that yields a value over 1,000. This works with numbers, it works with characters, it works with strings, it works for all those guys. It is more general. The imperative version searches only strings. The functional version searches any sequence. The imperative version matches just characters. The functional version matches any predicate that you send in as a higher order function, any combination criteria. The imperative version returns the first match. The functional version returns a lazy sequence of all the matches. This is one of the cool things in Clojure is that every data structure that can be is lazy. Meaning that you call it to get the first value, but now you can call it again to get the second value if you want. The Java version only gave you the first value. This will keep giving you values if you keep asking for it, but it never computes the values until you ask for it. So it's as efficient as it can possibly be. It gives you the option to call or keep calling them if you want, but it never computes them until you actually need them. That's laziness, and laziness is actually built in at the core of most of the data structures in the Clojure world. I'm sorry?
How do we avoid so the second time I call, I need the first value.
Mm-hmm.
So how do I avoid the lazy?
Well, you can always resolve those collections and make them eager if you want. So you can just say, I want the first few values from it, and you get those. So you can always turn them back into eager collections if you want. They just default to laziness, because that's a really useful thing. Because it does as little work as possible when you're trying to calculate values for something.
The requirement is the second call should return the second occurrence, should return the first occurrence.
Perfectly easy. I'm just saying that laziness is a feature. You don't have to use it. You can make these unlazy if you want and get as many values you want out of them, but you have the benefit of them automatically being lazy if you want them to be. So let's talk for a second about one of the really unique things about the way Clojure is designed underneath. And one of the reasons why I think that this is probably the best engineering language available on the JVM right now, because it solves a lot of really hairy problems. So let's look at state for a minute. And persistent data structures. All the persistent data structures in Clojure are immutable. In fact, everything in Clojure is immutable except for one thing, which is a reference. And you can change what a reference points to. But all values are immutable. So all collections are immutable, which means you never throw anything away, you add more to them. That may make it sound like it's very inefficient, but it's not. And I'll get to that in just a second. You change values by function application. All of these data structures maintain performance guarantees, even though they're immutable. And you always have old versions. One of the cool things about immutability is that you never actually remove anything, you just shuffle pointers around. So how can this possibly be efficient if I have things like maps that are immutable? Isn't it going to grow without bound really quickly? Actually, it's not because of the immutability. So for example, if I have a linked list and you have a list that has tern and rabbit on it and I have a list that has Neal, tern and rabbit on it, it's perfectly safe for us to share this data structure because it's all immutable. No one will ever change anything that I'm pointing to, and so that makes it very easy for me to share all these data structures in memory. And that's exactly how these persistent data structures work inside Clojure. You don't have to know how this works to use them, but it's kind of interesting to see. There's some interesting computer science around this, around balanced tries. And you can do the same thing we did with a linked list in data structures like this. This is a bit partition try. There's some interesting computer science about this. This is a simple example, but this would be too slow if you had real persistent data structures because it would have to dig really deep to get these things for a normal case. So that's basically log 2 of n. The way that Clojure actually does this is it uses 32-way tries. This gives you log 32 of n. That means that on average you traverse like 2 levels down before you find the value that you're looking for in your immutable collection. And so there are actually performance guarantees on this to make sure that they're very efficient. None of these collections grow without bounds unless you put unique values in there, but you almost never put unique values in collections. There's a lot of repetition, and so Clojure only stores one of those for any particular value. The other thing that Clojure does is basically fix threading in Java. And this is one of Rich's ambitions, was to make threading in Java trivially simple. In fact, Clojure does for concurrency what Java did for garbage collection. You don't really have to think about garbage collection in Java, and in Clojure you don't really have to think about multi-threaded access at all either, because the language handles that. And Rich figured out what makes threading so hard in Java is because of the way that variables were implemented in Java. Because variables were implemented in Java long before threads were implemented, and they made a lot of assumptions when they created variables that don't work well at all with threads. Variables are assumed to have a single timeline that they completely own. They can mutate their state at any time with no warning whatsoever without notifying anybody that something has changed. There's no good way to hold on to an identity for a variable because it changes. Basically, the problem is you've got several things conflated on top of one another. You have identity and state kind of mixed up together with variables in Java. What Rich did was tease those two things apart. What Rich did was create this extra level of direction called an identity. And an identity never changes. It may point to an immutable value at one point in time, and it may change to point to a different immutable value at a different point in time, but the identity itself never changes. Unlike a variable, it never changes its value, but it may point to something different. And what Clojure has done is said everything in Clojure is immutable, except one thing. A reference. And you have to let Clojure handle the assignment for the reference for you, and by doing so, it fixes concurrency problems, because inside Clojure, it's making sure that you have atomic succession and is in fact running a transaction engine to make sure that all your variables get set correctly. This is what is called the atomic succession model or the epochal time model. The square box here is a reference over time, and it holds a particular value at some point in time. You apply a pure function to it, and it gets updated to another value at some point in time. At some point, some observer or some memory is going to read, dereference that reference, and get what its value is. That is its state at some point in time. But this is the way that references work in Clojure. The way that this works in Clojure syntactically is you call a change state function on a reference, pass it a function, and then whatever arguments that you want. Snapshots always available, no user locking, no deadlocks, and writers never impede readers. The transactions, the software transactional memory stuff in Clojure is ACI but not D. It's atomic, consistent, and isolated, but it's not doable because it's in memory. But it works just like the transaction mechanism in your database, only this is working at your variable level in your code. So for example, if you're trying to update 3 variables at a time, let me show you the picture for this, for STM. Let's say that you want to make sure that both these variables get set or neither of them get set. You can wrap them both into a transaction and it'll automatically retry if it can't achieve one of them. It has some sophisticated stuff inside about barging. If there's something that's been retrying for a while, it'll actually bump the priority up on that to get it more eager to try to get a transaction to be successful. It'll go back and roll back and a bunch of other sophisticated stuff, all happening at the language level within variable definitions. So this will let you actually take an arbitrary number of variables and say, make sure they all get their state changed or none of them get their state changed, and it's guaranteed to work. The syntax for this is actually quite boring because all the magic is built in the runtime the way it works. So the way that you create one of these guys, this is how you create a reference. This defines me a new variable, which is a reference to an empty list. I can get the value back out of that reference if I want by calling the deref function on it. This is such a common thing. There's syntactic sugar in Clojure. If you call at messages, it calls the deref function for you and returns the value. So if I want to update a message, this is what an update message would look like for my little message holder guy. So I want to add a message. This is the new message I want to add. I want to alter the messages reference, conjoin this new message onto the end of it. Conjoin means tag this onto the end of this collection. But you'll notice here do sync. If do sync wasn't there, this code wouldn't run. I would get a runtime exception, actually, no transaction running, and you're trying to mutate a reference. And Clojure won't allow you to do that. Do sync launches it in software transactional memory, and of course this can be as many lines of code as you want inside this do sync block, and it'll make sure that all those things come true or none of those things come true before it finishes off that transaction. This is a very sophisticated mechanism inside Clojure. And in fact, there are really only two commercial software transaction memory implementations out in the world, in Haskell and in Clojure. And not surprisingly, both of those languages really prefer immutability. In fact, the .NET guy several years ago got ambitious and tried to build software transaction memory on top of .NET and then gave up because it's too difficult to do this if you have uncontrolled mutable state. So you're probably not going to see this in a language that allows you to do uncontrolled mutable state because it's just too hard to keep track of all the changes that are taking place. A language like Clojure or Haskell that controls mutability can do these really sophisticated things like software transactional memory. Questions about that? It's a very cool thing. It's one of the really unique things about Clojure is the way that it handles concurrency just pretty much invisibly to you. You never have to worry about, you never write the word synchronized. This is perfectly thread safe. And in fact, a lot of the collection classes now in Clojure will automatically, because you always know you have pure functions in Clojure, it will automatically stretch out across all the processes on your machine and take advantage of all those without you having to do anything. So you automatically get access to multi-cores just by using the data structures in Clojure, because underneath they know how to take advantage of these of concurrency, and you never have to bother yourself with it, which is nice.
Can you address the simple reader-writer problem in this case?
I'm sorry?
Can you address a simple reader-writer problem in this case and show us how it actually works?
A simple reader-writer problem, and show how it works? Well, I can't right now. I have it prepared and ready to show you right now, but I mean, it's a pretty simple thing. I mean, you can actually get examples of this. I mean, there are tons of examples of this on any of the Clojure books. I just don't have an example of that right now. It's actually trivially simple. There's no any kind of threading code in there. And in fact, you don't. In that case, you probably would not even use something like this. You'd probably use a future and a promise, which also Clojure has, futures and promises to handle provider-consumer stuff. This is not the only concurrency mechanism in Clojure. In fact, it has a really rich, there's an actors library in there. It has really rich promises and deferred futures and futures. It has lazy deferred futures, so that it doesn't try to resolve the future until you call it, and then it becomes a lazy collection for that future that comes back. So there's actually a lot of sophisticated concurrency stuff in here beyond just the STM stuff. I'm just showing that because that's so unique to this space. One of the things I talked about was that Clojure really wants to map back to the Java world as conveniently as possible because they realize that you need to get to things in the Java world. In fact, one of the kind of persistent questions is, well, you know, Lisp has been around since the 1950s as a language. And so there's an interesting question is, well, if it's so fantastic, why hasn't it taken over the world yet? Well, there are real answers to that question. In the very early days of Lisp, every Lisp has been garbage collected since day one. And in the 1950s and 60s, that was really slow, having garbage collected language on those hardware systems. Then they were all commercial, so they were very expensive to get into. And of course, the common Lisp is out there, and it's actually used in a lot of places. The problem with building a new Lisp, and Paul Graham actually did this, created one called Arc. Building a new language is simple. That's like a weekend project because Lisp as a language core are really tiny. But building all the stupid libraries to make it useful stuff, to connect to databases and talk to WebSockets and all that stuff, that takes man-centuries to write all that stuff. But that's where Clojure has a huge advantage because it can call back into all that Java stuff that's already there, and you only have to re-implement the stuff you want to re-implement in Clojure. So having that Java, all the Java back there, means you don't have to rewrite all these libraries from the ground up. And so I think that may be part of why this version of Lisp is getting a lot of popularity.
So how does that, Java is not, change immutable, right?
Yes.
So how is that handled in Clojure when we are calling the Java?
So when you're calling something in Java, you can mutate that because that's Java code, not Clojure code. So you have to be careful when you call Java stuff. So more to the point, you can't drag a Java object into software and transactional memory because that's mutable, and we don't do mutable stuff. You can take those values and put them into a reference and then put that in STM, but you can't just grab a Java object and stick it in STM because it's mutable. So there are some restrictions on things like that.
How does the immutability impact the memory footprint at the runtime?
Not at all. So I'll give you a good example of how much people worry about that or they shouldn't. One of the wicked cool things, so one of the things that Clojure is definitely going to be popular for is building sophisticated tools. There may be no more powerful language bang for the buck for a number of lines of code on earth. And the Clojure core guys have recently implemented a fascinating thing. You go look at it. In fact, you can play with it. It's free for up to like 5 connections or something like that, called Datomic. It's atomic with a D in front of it. It's an immutable database server. Think about that for a second. It's an immutable database server. When you put a value in there, it's always there. So your first worry is, oh no, that's going to just grow, just explode with values. But I've got a question for you. In your relational database right now, how many times does the number 4 show up? How about a bunch? Hundreds. What if you could store 4 one time and just store pointers to that 4 everywhere? That's how Datomic works. It stores values and then pointers to values, and everything's immutable, so it's safe. So it doesn't grow without bound. In fact, it keeps a pretty good boundary, and you can get performance guarantees on top of that. But here's another interesting question. Clojure being an immutable database means that everything you've put in it is always there, and you can get back to it later if you want to. So you've never destroyed any data. Using your relational database right now, when you do a destructive update, why are you doing that? Why are you destroying valuable trending data in that relational database? Oh, well, you know, we have to do that in relational databases because hard drive space is really expensive, and we want to maximize and use those little hard drive spaces as possible because that's really expensive and program time is cheap. Oh, wait a minute. A lot of the assumptions in our architectures now are based on 30-year-old thinking. Like, hard drive space is so precious that we're going to do destructive updates and destroy some of the data there so we can reuse that space. I got news for you. Hard drive space is not scarce now. In fact, you can get it for like a penny a gigabyte from Amazon now if you want it. It's dirt cheap. So why are you going through all these crazy hoops to get your relational database to work for in-place updates when, in fact, not only do you not want that now, that's actually the worst thing that you could have right now because you're destroying that data and you could never get it back. Why are you destroying all that data when you could keep it and do reporting and trend analysis and other sorts of interesting things on it? We're doing that because we're based on these old architectures.
When you actually do a delete, you're not deleting, you're just storing a flag.
Exactly right. It doesn't delete it, it just moves it away. Now, they've actually added a facility now to delete it for sensitive material, like if you have a password or something that you do want to delete, they can actually basically not delete it, but mark it over with other values, so there's a semantic for that. But in general, you just move the pointer away from it, but the value is still there. The value never goes away. Datomic also does this with schemas, so it actually stores schemas and versions them over time as well. So Datomic is actually a good example of the kind of fundamental rethinking of assumptions that you can do in a language like this and come out with tools that look nothing like other tools. Datomic's actually a commercial product, and I have clients using it now. It has a really sophisticated some mechanisms in it. And it's written in Clojure, and it's based on all these immutable ideas in Clojure. So I was talking about Clojure tries to map really easily between Clojure and Java. So let me look at data for a second. So you can create records in Clojure that look kind of like classes. In fact, you can compile these into classes in the Java world. So if I want to create a new instance of this guy, remember that's the constructor call for a Java class. So this creates a Java class with 3 parameters, and it gives you a constructor automatically. But here's an interesting thing. I want now to be able to get the value of B out of my data structure. Instead of calling a particular function here, the keyword becomes a function on the collection, which makes it very readable. I want the value of the B keyword from my function. Rather than calling something and passing 2 parameters, the keyword becomes a function on the collection, and you can pull values out that way. If I look at the class, this is just a plain old Java class. It actually implements a bunch of interfaces that Clojure adds to you to make it interoperability more easy. But you can now take this record, this class, move it over into Java and do stuff with it all day. This is indistinguishable from a class that was created in Java. But Clojure really prefers data in maps. And so Clojure would rather see it like this. This is a map with keywords and values. Everything works the same way, though. I can get to the last name like that with keyword access. I can actually get the nested access, say give me Stu's address in C and get Durham. I can go in and make a change to it, update it. Now when I do this, I don't destroy the Stu that used to be here, but I don't point to any anymore. I now point to a Stewart as part of that map. So that's a modification, that's an immutable modification. And I can do nested updates within that data structure. But what if I didn't want this in maps? Maybe I wanted it in records instead. I can do the exact same structure, creating a class structure, just like I have keyword access, just like I did with maps. I still have the same nested access I had with just pure maps. I have, everything works like it did before. So what Clojure's done is said, you can have a class hierarchy or you can have a set of maps, and I'm going to treat them exactly the same way. I like maps, Java likes records, we'll just make those interchangeable between one another and have one spawn the other whenever it's convenient to do so. So this is part of the mapping between the data structures that Clojure likes and the data structures that are native in Java. It does a really nice mapping between those things. You can get to the type information if you want to, but mostly this stuff just lives in maps. So I'll leave you with one little thing. I did a talk a few years ago at the Clojure Conch, which was about what it's going to take to get Clojure penetration in the enterprise. And I had all these strategies for how to get it to work. And about 6 months, well, probably a year after I did that talk, I got an unsolicited email from someone who had watched that presentation online, and I've reproduced some of his email with permission, hiding the company name and some other stuff. You'll see why in just a second. So he said, we recoded our flagship application, name redacted by request, from Java to Clojure about a year ago and never looked back. Why? Reduced our lines of code down by at least half. Support and bugs have likewise been cut by about 65 to 70%. We have large enterprise clients. How did we get Clojure into those very old guard environments? Between me and you, we lie. We don't talk about Clojure. We talk about Java extensions or the Clojure Java extensions. No one is the wiser. Clients love us for our blistering fast turnaround. We present ourselves as a larger company with fake LinkedIn employees. We only actually have 4 real employees, but with Clojure we do the same work as if we had 20 real employees. This is a company that does fixed rate bids, and what they discovered was they can deliver the work in Clojure with 4 people, but they can't get anybody to hire them with 4 people. It's like, well, this is way more work than 4 people would do, so they built fake LinkedIn employees to make it look like it's a 20-person company. And then people say, okay, this looks about right for 20 people, and they get it done with 4 much faster than they thought they could ever get it done. So they're not looking back. Clojure is a very powerful thing in the right hands. I don't suggest that you actually create fake LinkedIn employees, and particularly don't bill for fake LinkedIn employees. But I think it's interesting that the order of magnitude, or the magnitude of speed up is really amazing. Stuart Holloway with Relevance built this Clojure project for a client and sent it to them. They immediately sent it back and said that zip file is not nearly big enough to be the whole application. You must have left some stuff out. He didn't. So what he did was took 4 or 5 big fat jar files and dumped it in the zip file and then sent it, and they said, okay, that looks about right now. He didn't call any of those jar files, but he just did that. It looked like it was the right size project, even though it was just very, very small. So what's cool about Clojure? It's a really highly expressive language, really good Java interop. You can get to every corner of Java, but it doesn't compromise its engineering purity to make it easier to move from Java to here. It is very much a destination, and it is very opinionated. That's one of the things I like about it, because most of its opinions around how do you write really robust, safe software. It is a very good engineering language in my opinion. It's functional. That's the way the entire world is going, and this is a really good functional language. And of course, it has these really, really cool advanced concurrency characteristics. Any leftover questions about this before we call it a day? Yes? Testing's built into Clojure. There's a testing library built into Clojure. There's several additional testing libraries that are out there as well. So testing is a pretty good first-class citizen in the Clojure world. And there's the testing stuff is actually built into Clojure itself, so you don't have to get a separate framework or anything like that. And it works really nicely. You don't really need mocking libraries, stuff like that, because you can do that very easily with Clojure itself. Yes? Yep, that's an interesting question. Clojure Lisp is actually one of the very original DSL builder languages. In fact, our most interesting project in the world right now probably is this project we're doing in San Francisco at Anai. These guys have patents on targeted cancer therapies based on your genome and the genome of the cancer. And what they've done is trying to build applications that can figure this stuff out. They built it all in Clojure and Neal for J as a persistence mechanism, and they built a whole bunch of DSLs in Clojure. Clojure with macros is actually very easy to build DSLs, so that allowed the scientists to actually piece together the kind of experiments they wanted to see and run them in a sandbox to see what the results were. So the scientists were working at a very high level, very close to what they're used to, and these DSLs were actually doing all the work underneath to do the programming stuff. So this is actually a very popular host for DSLs. In fact, several of the persistence libraries that I showed you are actually implemented as DSLs on top of Lisp. So that's actually a common thing in Lisp for a while. Clojure is supported in JBoss. It's supported in Spring. You can actually take Clojure classes and put them in Grails and have Grails instantiate those guys for you. So a lot of this ecosystem stuff, it's all just bytecode. So a lot of this ecosystem stuff does work with Spring and things like that. Now, Hibernate's problematic because Hibernate assumes mutability everywhere. So you have to use a different persistence mechanism, but things like Spring and Grails work perfectly fine. All right, well, they're turning the lights up on me, so it looks like I'm out of time. Thanks very much for coming, and I hope you enjoyed it.